So during your lesson preview, did you notice that you could take this properties of logs and expand this into a nice log function? And wouldn't you rather avoid a chain rule when you could, especially a chain rule that involves a product rule in the middle of it? I think if we could avoid that, it would be nice. Did you also recognize that the expression that it gave you was actually the derivative of the natural log of the quantity x plus 1? And this function was evaluated at x equals 2. So this was another natural log function, just an easier way to write it. Now, you've already looked at the log properties when you were in pre-calc. I also asked you to review them a couple weeks ago. So this page just is a reminder of all the different properties that are going to be interesting to us. I also wanted to take time to prove to you what that natural log's derivative is. We've already talked about it. The derivative of your natural log of x is equal to 1 over x. But of course you want to know why. So let's go back to the definition. We get the limit as delta x goes to 0. F of x plus delta x minus f of x, all divided by your delta x. Then if we take this limit as our delta x goes to 0, do our substitution, we get the natural log of x plus delta x minus natural log of x divided by your delta x. But after that, we're going to use those properties that you just looked at for a moment and rewrite this as the natural log of x plus delta x divided by x all over delta x. Now, from here, what we're going to do is a little bit more log properties. So we're going to take the limit. So your delta x goes to 0. Think of this function as 1 over delta x times natural log of x plus delta x over x, in which case this term becomes an exponent. So we have the limit as your delta x goes to 0, natural log quantity x plus delta x all over x raised to the 1 over delta x, which looks a little bit crazy. So let's do some more math. We get the limit as your delta x goes to 0, the natural log of 1 plus delta x over x raised to the 1 over delta x. And you're asking yourself, what is going on here? So, you know what? Let's think about this some more. What if we were to do some substitutions at this point, just to make it look nicer? What if we were to let y equal delta x over x? And in that case, that would imply that x times y is equal to delta x. So now we're going to rewrite the entire problem again, which will give us the limit as your delta x goes to 0 of the natural log of, well, what's happening here? 1 plus, that's how we defined our y. And then that's going to be raised to the 1 over y. Now, stop and wait and, 1 over xy. And then think about it a little bit more as you're looking at 1 over xy. What if I did it again and used a log rule? Rewrote this as the limit as delta x goes to 0. This time, I'm going to bring the 1 over x in front and be left with the natural log of 1 plus y to the 1 over y. Then apply your definitions for me. If we're looking at delta x going to 0, that means that the xy is going to 0. But x is, I'm going to hold that constant and just think about this as your y value going to 0. So think again, what is the limit as y goes to 0? The natural log of 1 plus y to the 1 over y times 1 over x. You got it, guys. If you recognize this as the value of e, then you are an awesome math student. So what we now have is this is equal to the natural log of e times 1 over x. And since once again we apply another property, the natural log of e is 1, that tells us that using our definition of the derivative of the natural log of x is 1 over x. And that was super. So now you have a proof for the derivative of the natural log. You can use it anytime, and we actually want to make this a little bit better now. That's why we're looking at it a second time. The chain rule can be applied. The derivative of the natural log of u is 1 over u times your du dx. And I also know that the natural log of the absolute value of u is going to give me the same thing, because when you're playing with those absolute values, remember, the argument of the log must always be positive. So if you're looking at the absolute value function, you're only playing with the positive component. We also have rules for log functions, the log function, and the proof for these rules is also based upon all of your log properties. So take a look at these log rules, 1 over log a times x, and then of course you have to apply the chain rule at times. So you have 2 new rules to throw into your list. So of course the problems we practiced today, we're going to have to use our log properties and our chain rule. So as I look at my first problem, this is the natural log of 3x. The argument of the log is the 3x. The derivative is 1 over the argument times the derivative of the argument, which is 3. So we end up with a 1 over x for this derivative. There were actually 2 ways to do this problem. If I were to ask you for the derivative of the natural log of 3x, I could have used a log property and rewritten it as the log of 3 plus the log of x. But you know the derivative of a constant is 0, and then the derivative of your log x is 1 over x. So each time you look at a problem, you should decide whether you want to use algebra to simplify or just go straight for a chain rule. Now the second problem, we're definitely going to split this up using our log properties. We have x minus 4 within a log plus 1/5 times the natural log, the quantity x cubed minus 5. So always try algebra first. After you try some algebra, next thing we're going to do is apply calculus. So it's 1 over the argument times the derivative of the argument, which is 1, plus 1/5 times 1 over the argument times the derivative of the argument, which is 3x squared. Clean it up just a little bit. 1 over x minus 4 plus 1/5, 3/5 x squared, all over 5 times x cubed minus 5. So double check that you have your coefficients correct. Oh, look at this one, guys. Example 5 is an example of implicit differentiation. Now, of course, we're going to use a product rule for this first expression because it says x times the natural log of y plus 1. And then we have 2y squared equals 5. We're looking for dy dx. So let's start with our product rule. We have first times the derivative of the second. Now concentrate on the second. That's going to be 1 over y plus 1 times dy dx, plus the second times the derivative of the first. With respect to x, that's just 1. Plus, chain rule, guys, 4y dy dx equals 0. Remember, our goal in this problem is to solve for dy dx. So dy dx is going to be factored away from the rest and will equal negative natural log of y plus 1 divided by x over y plus 1 plus 4y. Now, you know perfectly well complex fractions are not acceptable. So we're going to multiply this expression by y plus 1 over y plus 1 in order to clean it up. And we will get negative quantity y plus 1 times the natural log of y plus 1, all divided by x plus 4y times y plus 1. And then it's your choice if you want to distribute the 4y. But I'm going to stop right there. This will equal dy dx. Oh no, guys, I couldn't resist. I'm sorry. Example 6 is a radar problem. We have a radar antenna making 1 revolution every 5 seconds. It's located on a ship, and the ship is 6 kilometers from a straight shoreline. How fast is the beam along the shore moving when the beam makes an angle of 45 degrees? So how fast is the beam moving along the shore? So we want to draw the shoreline first. So I draw it here. There's my shoreline, guys. I say so. Now I have my boat or ship right out here. Now it has an antenna on it, and the antenna is revolving 5 seconds, 1 revolution every 5 seconds. Okay, so I don't even have an angle. I have no variables. I'm going to have to do some more work. I have to draw more on that picture. So let's see here. What else do I know? That the ship is 6 kilometers from the shoreline. So I could draw that in. 6 kilometers right here. And that's not moving, so 6. But the beam is what's missing. So I'm going to use this yellow to represent the beam of light. Let's say it's a light ship. And there's the angle that's being created. So we know that this radar antenna is making 1 revolution. Since I've called it theta, now I know what to write. So I know that d theta dt is given to me as 1 revolution every 5 seconds. Now, revolutions per second is not very useful, but I do know that that's 2 pi radians every 1 revolution. So now I have 2 pi over 5 radians per second. Think about that for a minute. Revolutions are not good enough. It needs to be in degrees or in radians. And since this is calculus, I like radians. The question is, how fast is the beam moving along the shoreline? Now look at your picture. I have 2 ideas. It could be what I'm labeling X, or it could be what I'm going to label H. Which one is the beam's path along the shoreline? So that's going to be X. So the question is asking for dx dt when theta equals 45 degrees. And if we don't like 45 degrees, we can write that as pi over 4. All right, so we have our question. We have our picture. We just need, look at this. It looks like a right triangle to me. Does it look like a right triangle to you? And I need the adjacent. I would rather skip the hypotenuse. So if I'm thinking about my adjacent and the opposite, that sounds like SOHCAHTOA. So the tangent of theta is equal to the adjacent side, which is 6, over the hypotenuse, which is x. All right, now we have choices. I could cross multiply to do some algebra here, or I could just write this as tangent theta equals 6x to the negative 1. I'm going to go with that. Now, the derivative of tangent is secant squared. Here's my theta. Then I have d theta dt is equal to negative 6 x to the negative 2 dx dt. Don't forget that dx dt needs to be in there. All right. Do we have all the variables we want? Do we have theta? Yes. Do we have d theta dt? Yes. Do we have x? No. So what do we have to do? We have to find x. That's going to be our next job, finding x. So go to your relationship. We know that the tangent of theta is equal to 6 over x. Well, then x is going to be equal to 6 over the tangent of 45 degrees. And we know that the tangent of 45 degrees is 1. So x equals 6. That wasn't so hard. So we now need the secant of squared of 45 degrees d theta dt, which is times 2 pi over 5, that's pi over 5, it's going to be equal to negative 6 over x squared, so that's 36, and then dx dt. And from here, you can solve for your dx dt, and you will be set. Don't forget to write a sentence. The beam is moving along the shoreline. What are we measuring in? Since the shore was measured in kilometers, your dx is going to be in kilometers, and t, of course, is going to be seconds, so kilometers per second for number 6. Make certain you read the directions carefully. We're only working on the even questions, 42 to 54, and then you're going to have a couple questions to pick and choose from this page. So just follow the directions, please, for your lesson practice.